power of vibration analysis is the presentation that I would like to do today for you. I should start with a little about my background, that is in electronics engineering, and before I now working in SINTEF Digital in demanding environmental group at a smart sensor system and microarchitecture. The strategy that we follow is asset management and condition-based maintenance in our group. And it is now about 5-6 years that we are developing condition monitoring systems for some kind of specific applications that there is no solution for them in the market, like in downhole systems or in the process for industry or in transportation, like on bogies of the train. And I would like to start this presentation with first with an overview of the equipment reliability, and then an introduction about vibration analysis and CBN, the benefits of vibration analysis, and what challenge in vibration analysis that we need to address, and leveraging edge computing and AI in solving those challenges, and finally give some information about the project that we recently delivered to our customer, Montana Rail CBM project. Equipment reliability is predicting the time that a piece of equipment will correctly function, and we can with good estimation say that, okay, in like next hundreds of hours or thousands of hours, this equipment doesn't fail. And the time the equipment runs without failure is like another definition of this term. However, for doing this calculation, we need something failure rate. We need to have this parameter. But if you have a look at this curve, that's this value of failure rate is very well known. We see that in the beginning of an equipment comes out from manufacturer factory, then the failure rate is quite hard. That it's infant mortality of the equipment, and then for a while we have almost fixed failure rate for most of the equipment. And what is happened usually is just random failures in this part, and after a while, then we come to like wear out phase of the equipment. That failure rate starts to increase, and it means the aging of the equipment is happening. But in between this useful life is the place that we can consider with like good approximation that we have a fixed failure rate. There is another term, mean time to failure, that is similar to reliability, but the average time between failures is the definition of that. Dividing the total operating times by the number of failures is how we calculate it, the MTTF. But while it is a very critical reliability metric, it doesn't give exactly what is happening in a good estimation about what could happen during the time, because we can see later that many of devices can fail before or after that. MTTF is often utilized to predict or estimate the reliability, but MTTF does not provide information about the failure pattern or the distribution of failure times. If we consider exponential distribution for the failure and the fixed failure rate like lambda, we can see here that we are in this kind with this in this part of the graph, and with fixed failure rate, we see that more than 63% of units will fail before reaching MTTF, and about 40% of them can continue even after MTTF. So MTTF, just while it's a good to compare two different devices, but it is not a good metric uh, uh, to say that one instance of equipment, how we can predict that exact instance to work for a while. It can fail quite early or before that, but it's still good metric for vendors to use that to make something that we talk about, scheduled maintenance later. To solve that problem, preventive maintenance invented, and then it is what we know as planned maintenance or scheduled maintenance. We have a plan is usually provided by the vendor, so the vendor uses statistical data and from previous failure and from the several instances of the equipment to say that to be in the safe side when you should do the repair and which kind of repair on this equipment. And it is scheduled maintenance, so it could be based on the time, based on the service of that equipment. For example, if it is a generator based on kilo megawatt watt hours that it has generated all the time, or if it is like a train bogie based on the kilometer that it has traveled, or again based on the time, like 2 years or 1 million kilometers, what happened the first. Then it minimizes the unexpected equipment failures and downtime. That's good, but it extends the equipment lifespan and maximize return of investment and improve the safety and reduce the risk of accidents. All of them are good, but if we refer to previous slide again to the MTTF that was baseline for making a preventive maintenance plan by vendor, we see that it is we have a big part of the graph that is out of our control. After MTTF, like 40% of instances can continue after that, and even after the MTTF, and too many vendors to be in the safe side because of the guarantee and other things and reduce the downtime of the equipment. They don't consider MTTF as the baseline. They consider like 60% of it. So you can see that you have another 30% that comes to the device, the instances that can continue after the scheduled maintenance, and it means increasing the cost of the maintenance, and you have lots of unnecessary maintenance jobs to do that have lots of environmental effects. Like, just imagine you have a gearbox that you need to change its oil, and it needs gallons of oil, or you have a turbine that you need to this part of it and do regular maintenance on it, overall maintenance on it, and then assemble it again. And it increases the risk of the failure or human failure during doing the overall job. So predictive maintenance came with this idea to save those part of equipment from unnecessary repair or maintenance jobs. And plus, if you see, if you look at this graph, you see that the predictive maintenance can find the potential failure quite early. And if we have condition based maintenance, so we continuously monitor the device, we can let the equipment to do its service, and when we see that it's very close to a breakdown or needs really a repair, then we do the repair there. So we can save lots of time, and in this time could be like 1 or 2 overall. So it is not like 10% or 5%, something like that. It could be quite significant time. Plus, it is also possible while in the preventive maintenance, we were conservative to catch lots of failures before they happen. But again, it's possible that some failure randomly happened because we had a fixed failure rate. In predictive maintenance, when we use a condition-based maintenance, we can find the status of the system or equipment, and if a potential failure is possible to happen, we can find it before it happens, even before preventive maintenance. So it increased the safety and also the improve the cost efficiency of the maintenance program. But vibration analysis is one of the most important parts of predictive maintenance, and it's the idea is based on finding the fault in the equipment or system by analyzing the vibration that all the system generates and catching it by different type of sensors. Vibration is often an early indicator of failure. We have several types of indicators of failures, like temperature or sound or things like this. But usually what happens in many of equipment is that vibration is the first moving indicator that we can detect it. So we can predict the failure far before it happens in reality. And vibration analysis is a technique used to assess equipment condition as well. So that's very good because we can give it as an input to our model to calculate the health condition and do the prediction for the failure. And another thing is that identifying abnormal vibration could be done by instance for even one type of equipment, that it is somehow different from several kind of other methods, and is very well defined for machine learning and pattern recognition algorithms. Vibration analysis systems is a combination of some blocks that starts with sensors and transducers. That could be accelerometers, could be velocity or displacement. Data acquisition units that there are different range of them, portable or fixed online system or offline systems. Signal conditioning that in some systems is integrated in the sensors, in some systems it is integrated in data acquisition. And the data analysis software that mostly starts with applying an FFT on the signal, and reporting and visualization and vibration analysis that is actually today is probably the most important part of this system. The expertise of people who do the analysis on vibration on each machine, and they need to have this to gain this expertise not only by studying or attending the course, but also by studying a specific kind of equipment that we are they need to work with them. For example, if they work in a process industry, the equipment and behaviors, vibration behavior could be completely different from like transportation or maritime industry. Here I think I should give some examples about vibration analysis and how does it work for like bearing fault detections. In bearings, we can have faults on outer race, inner race, on the ball itself or the cage. And any of them has a specific kind of frequency or vibrations that they generate. And I got to show here, we have a defect on the outer rays here. And you see that when during one rotation, each ball that pass over this defect, we have a like bang on that noise that generates by that defect on the spectrum. And if what I want to show is that I will come back to it later, but it is important to see that when there is no issue, we have quite low spectrum from 1 kilohertz to 30 or over 30 kilohertz. And why the problem happens and defect happen early when we are quite early, we see that the spectrum comes going high on higher frequencies, and by the problem being worse, this high frequencies being shifted to even lower frequencies peaks, and then we see that even comes lower, and then we see some kind of peaks at quite low between 2K to 5K frequencies, and then we see that in velocity spectrum when it is being worse and worse. So what is important if we want to detect for equipment quite early, the problem that happens is that we be able to detect them at high frequencies. Because when they are coming to low, it means that we are very close to a breakdown or failure that it makes difficult for planning, for assigning the resources to do that. And finally, we see that in the velocity spectrum, we see lots of peaks, and then it is time to just change. In the gearboxes, we have another kind of spectrum. We see that, for example, in this gearbox, we see that 1x is the input shaft peak, and 1xp is the shaft peak at the output frequency, and we have a gear mesh frequency with some sidebands that usually are quite low. But if we have one with problem, then we see that this gear mesh frequency can be duplicated or go to third or fifth harmonics with higher sidebands that coming higher. And then if we have a resonance there, then what happens is that we have a natural frequency as well coming. So we can detect several different problems based on the spectrum, and due to that, we need expert people and the people that not only know the vibration analysis, but also know each equipment very well, and that's the behavior of that equipment for a specific industry very well. Then they can do their job very well. So it's the reason that we need to that we want to say that vibration analysis is very expensive in some cases. That yeah, we should find a way to solve that. Benefits of vibration analysis are first, early fault detection, cost saving, reducing unplanned downtime, emergency repairs, and production losses, and efficient resource allocation. When we know that system is going to be worse and worse and we need to change it, we can allocate resources in advance, and optimal spare parts management, minimization of unnecessary maintenance activities. That probably was the first aim to do that in predictive maintenance. Improving the safety is another benefit of it, and compliance and regulatory requirements in some cases, like in maritime or in transportation, there are some regulators that force to do that in a routine way to be sure that critical equipments are under control and we observe their behavior. But there are some challenges as well in VA and CBM, because data quality and interpretation is very important. So if every time that we want to do the vibration analysis, we need to attend the sensors in places, and if the place is being a little different, it could have some effects on the data that we get. So for critical systems, it's possible that they use online monitoring, so they fix the systems for those and don't move the sensor. Based on establishment is also another issue, because if we jump in the system and just get the first vibration, it's usually difficult to detect the problems from the first vibration. So we need a baseline from when the system came out from the factory and installed in place, and that is like a fingerprint of that system, and it's very important to know that. Equipment accessibility. In some industries, it's not easy to access the equipment to do this vibration analysis unless stopping the production line or something, so it has other costs. False alarm and false negatives that happens, and it is another reason that we need really experts to do that. And integration with maintenance practices. Scalability and resource allocations in finally is one of the showstoppers in using vibration analyzing and CBM on all equipment in a company or in a plant, both for the cost and also for the lack of resources, that we don't have enough experts to do everything. So what we did in one project, and it could be scaled to and be used on other projects, is leveraging edge computing and AI. We target the permanent installation, so we don't need to change the sensors on the equipment. The system should be battery powered, it should be wireless, and evaluating the raw data at the edge should happen, because even with our modern wireless system, we don't have enough bandwidth and enough power to send all the raw data that we read from the sensors. In some cases, in like many cases, it is good to have like 40 kilo sample per second to reach like 17 to 18 kilohertz of bandwidth. But in some cases, we need to go to up to 100 or 150 kilo sample per second. So even with 40 kilo sample per second and with 24-bit resolution, it is not possible to send all the data outside or with a good wireless and battery budget. And finally, if we can compute all the results on the edge close to the sensor, we can apply the FFT on the data, then feed it with machine learning algorithms, and then send the results as a category of the health condition of the equipment to the cloud, and then we can save the bandwidth and power and everything. The good thing that happened is that we are always able to update this system that is process the data. So based on the other units that are in the same plant or environment, we can update this machine learning models and processing system. So we can get better and better information from that. But Rail CBM project that we have delivered to Montana was an example of this kind of system. We made a system that were installed on trains and read the data from bogies with almost 300 kilo sample per second with 24 bits from 16 different sensors from each bogie, and then correlate that data with GPS, IMU data, and applied some machine learning algorithm on it, and send the results as the health condition category to the cloud. Here we have the type of sensors that were connected to Boogie Deck, and actually this one is mostly a terminal box on the being installed on the Boogie, and then we have another box in the train that I will show you later. Yes, train deck. It's the box that we put on the train, and it has 8 channels. Each channel can accept 2 different sensors, and all of them are programmable, so we can select between accelerometer, velocity sensors, or temperature sensors, or even microphone, ultrasound microphones. And we have high-speed ADCs plus FPGAs there. So all the machine learning algorithms and edge computing stuff will be deployed on FPGA, so we can save the power and also run it with quite fast, because some of these algorithms are quite complicated that we need a high performance PC to do that. But in FPGA, we put them, we deploy them on hardware. ADC backplane board that we designed. We also made a tailored power supply that was certified for train railway sector, and input boards that are quite flexible to accept different type of sensors. And we got some signals from test bench in Growroot from Montana, that we can see that our system is able to detect the signals quite close together, but with more than 60 dB difference from the level. So it is very good in finding those signals. And we checked also the sensitivity on even smaller signals with and while they are close together with very strong and very weak signal, to be sure that there is no crosstalk, and it was very good. Actually, we got like 8 dB better signal to noise ratio than the lab systems that we had here from Kista. The collaboration was between SINTEF Digital, a smart sensor system, and Microsystems, Yun Bedum, Yurtur, Anish Liberud, Mortendro, and me, Mostafa Koraei, and mathematics and cybernetics, Milan, that did lots of work for machine learning algorithms and AI, and Carlo Manino from optimization group. And Montana OS, that was our customer. Yes, thank you.
Thank you so much, Mostafa. This was a thorough and well-prepared presentation. Some questions. You mentioned about that you needed experts and it was expensive to work on analyzing of data and so forth. But if I'm not mistaken, as long as you are able to include AI solutions, and you can also most likely use low-cost accelerometers, you should be able to have a very low-cost system and still have a very fruitful detection of predicting occasional failures. Isn't that correct?
Yes, exactly. It is the reason that we introduced this system that is a combination of sensor, ADC, FFT, and AI machine learning stuff on the edge. Yeah, to do that. And the good thing is that this system can be better and better by getting more failures and finding more problems in an environment. So if we have, for example, 100 of machines, similar machines like electromotors in one plant, they could have very similarity in that plant, but they could be different from the same type of machines that working in another plant, and this system can detect that different or differentiate between those kind of vibration and give better information or better categorization for that the machines that are working in that specific plant.
So in a bigger plant, like in a production process of metal industry or something similar, where you perhaps need to have hundreds of accelerometers, one should be able to build this together and still have a very automated and not costly solution as well.
Yes, exactly.
That's what I was thinking of. And one more thing, these sensors are also very detecting of any kind of signals around it. So if I understood you, to measure the boogie and the prediction of maintenance for the boogie itself, it might also detect any kind of failure on the railway itself. Isn't that something that you're also looking into?
Yes, the good thing for vibration analysis is that the vibration can travel on structures and so on. So if we have a system that is deployed on several units, like what we did in the Ray CBM project, then you can detect the vibration that are not necessarily coming from that the unit that you are observing it. So in what happened in that project is that finally another customer came to our customer, Bannerur, collaborated with Montana, and they asked for that data. That is very valuable for them because the vibration that we detect is coming not only from the bogies but from the railways as well.
Thank you so much, Mostafa. Before we getting close now to the end, is there any questions you might ask? Yes, please, Adlan.
Yeah. Hello, Alnunan Bjørstad. I'm from Elkem. I was wondering how sensitive is this, because you were talking about how the vibrations travel to everything. So if I have a truck driving through my plant where I have these sensors, or some other piece of machinery like a transformer that is shaking or something, how does this affect the measurement? Can you isolate that?
We can, yeah, you probably this system is quite sensitive. So the sensitivity is like in the range of minus 130 dB. So you definitely detect the trucks or transformer or any kind of vibration in that area. But what we do is that we use our signal processing to isolate that vibration from the vibration that we want to detect from the target equipment that we attach the system to that. So yes, when we attach the system to the bogies, we detect lots of vibration from all over the terrain, but we isolate them in a digital board, not in the. We cannot isolate them at the sensor side, but we can isolate them on the edge computing system. By what we just need to know is the mechanical structure of the system that we are measuring the vibration in, and also about the speed of the main rotating parts of that system. Or it is the direct way, or we can also do some signal processing to detect it indirectly on the signal and then isolate those parts from the rest of the vibration.
Yeah, okay. Thank you very much. Just one more question. How big does the signal from the bogies have to be compared to the external noise, like to be able to detect it, or separate everything out?
Okay, in some I should refer to this slide. This one, yes, it is a little bit short, but I can explain it here. Here we have actually applied external noise here. So what you see at more than 125 dB is not the or what we were looking for, it is the external injected noise. But what we were looking for is these two red dots that are close to that. So I think it is 9.44 and this one is 9.3, something at very close frequencies, but with 70 more than 60 dB difference. So if the external noise is in the range of like even 10,000 times higher than the noise that we are looking for, we can detect that.
I think it's also correct to say that this is very much due to what kind of sensor you're using, the electronics, the filtering, how you are able to remove the 50 hertz noise that is also applied. So when all of that is optimized, I think you can detect not a mouse, but you can detect quite a lot of this noise from a truck. That will be that shouldn't be easy to detect. Yes.
Yeah, okay, thank you very much. It's very interesting.
Any other question? Could we, before we round off, can we also say that the biggest problem with accelerometers and these kind of measurements is the amount of data it develop, and so it is so vital, and also the reason why so many are focusing on edge computing and be able to compare the results and the trends at the place of the sensors, and only transmit data when there are changes or aviations or detect errors. Because if you think about that, you have perhaps 100 of these accelerometers in a production. We are talking about terabyte, not only per hour, but this becomes an extremely amount of big data. So we have to be very cautious on how we treat it and how we can minimize it.
Yeah, I can just point that for 8 sensors, we had around 100 megabytes per second. Yeah.
So so you don't send that to cloud. Then it would be extremely expensive. Yeah. You need to do the filtering before you do that.
Yeah. So the whole purpose of using AI and machine learning at the edge with FPGAs, we're processing that data at the edge and just sending the results to cloud.
And it's also very interesting now because something is happening in this industry. There are coming microcontrollers which already have AI solution in it. So you can really on the edge, almost on the sensor with the transducer of the accelerometer, be able to do the filtering and the analyzing. And then this is minimized, and then accelerometer becomes even much more of interest. Thank you so much, Mostafa. I think we just run off here now, and if there's no more questions, thank you all for attending this presentation, and thank you, Mostafa.
Thank you, Andre. Thank you.